Hi everybody, welcome back. What we're going to do today is talk about Chapter 5, which discusses the normal distribution. And for this particular video, we're going to focus on Section 1, so we're essentially talking about Section 5.1. The normal distribution is very important for understanding inferential statistics. So right now, remember, we're talking about probability, we're going to start talking about the normal distribution, and you're going to be learning important concepts for understanding inferential statistics. So give me a little bit of leeway here. You won't always understand the connection at this point, but you're learning important skills, important information that we're going to put together very soon for doing inferential statistics. So let's jump right in and learn about the normal distribution, and we'll start by talking about some examples. So, for example, is it normal for a baby to be born more than 2 weeks early? Well, let's look at some data. What this is showing is a grouped histogram of 300 hypothetical birth dates relative to their due dates. So how early or how late are these babies being born? And each one of these bars represents a width of 4 days. So for example, this bar right here represents babies that are born up to 2 days after their due date or 2 days before. And we can see that most babies, when we're looking in here, are born somewhere right around their due date. It's pretty rare to find babies that are born way late, and it's rare to find babies that are born very, very early. Well, let's answer some questions about this in particular. If we look at this one bar right here, this will kind of serve as a cutoff point regarding the question we were asking. Is it normal for a baby to be born more than 2 weeks early? So here we have 14 days early. So this bar would kind of represent that point. So let's just learn a little bit more about that for a second. This is showing, when we look at the frequencies, about 21 births that were up to about 14 days early. And specifically, this would show 10 to 14 days early, because remember, each bar is a width of 4 days. So this bar represents 10 to 14 days early. So we're just trying to understand this graph at this point. Here we'd see that 21, because again, I'm looking at the frequency column over here. 21 births were between 10 and 14 days early. So that's the frequency. And if we want to figure out the relative frequency, we'd look at that 21 relative to the 300 births. So here, 21 divided by 300 would equal 0.07 or 7%. And that makes sense because when we follow this bar out this way, we can see that the relative frequencies are charted, and that's about 7%. So again, we're just trying to make sense of what we're seeing here in this graph so that we can answer this question. All right, again, trying to make sense of what's going on here, we can see that the mode in this particular set of data centers right around 0. So most babies are being born right around their due date. And we can kind of ask a question, you're like, what is typical? Well, that's somewhat subjective, but most babies are being born right around their due date, so they're relatively typical. And we would say that babies that are born very early or very late are not very typical. So let's look specifically. What proportion of babies are born greater than 14 days early? And if this point right here represents 14 days early, then all these babies in here represented with these bars are showing births that are more than 14 days before their due date. So all that we would need to do at this point is sum up all of those relative frequencies if we're trying to figure out the proportion of births that are greater than 14 days early. So I can find this relative frequency right here, for example. And if I move out here, I can get a sense of what that value is. And that turns out to be 8%. I've got the actual values. So about 8%. This bar right here turns out to be about 4%. So I'm just going to list those all right over here because we're going to want to sum up all of the relative frequencies for these bars. And then when we look at the total of all these bars, that will give us the answer to the probability of births being more than 14 days early. So if we were to add all these up, we would find a value of 0.21 or 21%. So the probability of a baby being born more than 2 weeks early, that's more than 14 days early, would be 0.21 or 21%. So again, just to kind of summarize, approximately 21% of births occurred more than 14 days before the expected due date. And if you think about it, 21%, we're talking about 1 in 5. 20% would be 1 in 5. So really, it's somewhat common overall when we look at this particular chunk of births that a woman would be giving birth 2 weeks before her due date or even before that. About 1 in 5 chance. So what we're learning here is that we can compute probabilities based on looking at where the data lies in the normal distribution. Let's go ahead and take that a step further. Let's make sure we're understanding about this normal distribution, because if you notice with the data that we are looking at regarding these due dates, it forms, if we were to smooth things out, this bell-shaped curve that you've probably heard about throughout your life. Statisticians would call that bell-shaped curve a normal distribution. And normal distributions, regardless of what it is we're measuring, in this case we're looking at births and when the baby was actually born, they share various characteristics. So one thing that we see is that the data in a normal distribution is unimodal. We have this one peak, unimodal. Another characteristic is that these normal distributions are essentially symmetric. Again, if we were to cut this right down the middle, one side of the distribution essentially mirrors the other side. And again, we're kind of smoothing this out for presentation purposes. If we have a symmetric distribution, it means that the mean, our sample mean, x bar, the median, and the mode will all be equal. So right here, right at this 0 point, when babies are being born at their due date, is where we find the mean, the median, and the mode of our data in a symmetric normal distribution. And another thing, another characteristic regarding normal distributions, the variability of those values forms that characteristic bell shape that we were talking about. So by looking at this shape, we can get a sense of how much variability there is in the data. Remember, even though the mean, the median, and the mode is equal to 0 in this case, meaning that most babies are being born right there at their due date, there's some variability, right? Some of these kids were born very late, some of these kids were born very early, most of them were born somewhere right around their due date. That's what variability is all about. So these middle scores in here are very common. These scores in the tails of the distribution, we call these tails. The scores in the tails of the distribution are actually relatively rare. So that's one thing we're trying to understand here when we look at these normal distributions is what are the common values, what are the common birth dates, what are the rare birth dates. Common birth dates, they happen a lot. Very rare birth dates, they don't happen as much. Relatively speaking, of course. Let's get a little bit more information going here. Not all normal distributions are equal. For example, here you have 2 examples of normal distributions, but clearly they're not the same. Although they're sharing the shape characteristics that we talked about, I mean, they're both forming kind of, bells. They both are unimodal. Although they have those same shape characteristics, they have different variability. And variability is measured by the standard deviation. So standard deviation is going to become an important measurement for what we talk about. So if we understand these shapes and these distributions, we can answer some basic questions about the variability. Which distribution has more variability between the scores? In both cases, we can see the mean, the median, and the mode is equal to 75. It's right there in the middle of this symmetrical distribution. So literally the mean, the median, and the mode are all equal to 75. But there's more variability in one of the distributions. How can we tell? Well, can you see in this distribution the scores are more spread out? This modal value is actually lower in this distribution than this one, lower in frequency. There are fewer values at 75. Here we have more values at 75. Well, if there are more values at 75, there's less variability. More of the scores equal 75. So here we can see that there is more variability because the scores are more spread out. Here we can see that this distribution is more narrow, showing that there is less spread between the scores. Spread and variability are the same type of concept. Which distribution has a larger standard deviation? Well, this distribution would have a larger standard deviation because what does the standard deviation measure? On average, how much do the scores differ from the mean? Well, on average, these scores differ more than this mean. Over here, we see that there's less variability from the mean, so the standard deviation would be less. All right, so again, what we're trying to do is just understand some basic characteristics of these normal distributions so that we can eventually compute some probabilities based on those distributions. Let's go through a little thought experiment here. In this histogram that we've been looking at regarding childbirths relative to their actual due dates, it was really based on natural births, this data that was produced over here. And it is fairly symmetric. But today, most of you probably know, doctors will usually induce birth if a woman goes too far past her birth date, her due date. And that's because, as I understand it, it gets kind of dangerous at that point. How would the shape of the histogram change if it included these induced labor births? Well, let's think about that for a second. If we included not just natural births, but also these induced labor births, we would start to see that many of these births that would naturally occur in here would actually start occurring right around in here, because doctors would probably decide to induce the labor somewhere around the actual due date or shortly after that. So we'd start to see less data in here and much more in here. So we're always going to have some of those early births, there's not always a lot that we can do to prevent those. Oftentimes they occur without any expectation, but there's a lot that we can do to prevent these because we can induce labor. So we'll stop seeing as much over here, and then these births will kind of pile up at this point. So it's likely that we'd start to see a distribution like this. And right over here, again, we'd see that most of the births are right around the due date. It'd be very rare now to start seeing due dates that are very late. And ultimately, that would give us a distribution that looks like this. And when we look at this tail of this distribution here, we can see which way it's pointing. It's pointing to the left. And we've learned that that's a left skew or a negative skew. So in that little thought experiment, we see that we'd go from a relatively normal distribution to probably a skewed distribution. All right, so again, we're just trying to understand some basic characteristics of the normal distribution. Well, let's put some of that information together and answer some other questions. Here we can see that the area under the normal curve corresponds to all the relative frequencies. So if I were to add up each bar by looking at its relative frequency, if I were to add up all those bars, it would equal all the area underneath this curve that I've drawn in here. How much area is there underneath the curve? 100%. There's 100% of the area is underneath the curve. And if I were to add up all those bars, these relative frequencies would equal 1 or 100%. And that's the point that I'm making right here. The relative frequencies must sum to 1 or 100%. So the total area underneath the curve must sum to 1 or 100%. And what that means is something kind of neat. We're essentially able to compute probability between any range of scores by finding the area that's located underneath this curve associated with that range of scores. So just to say it in simpler language, the area underneath the distribution is equal to the probability of falling in that range. Area equals probability. We are going to be able to answer questions about probability, like what's the probability of a person giving birth somewhere between their due date and 60 days later. We can answer that question by computing how much area there is in this section of the distribution associated with births from that due date, the original due date, and 60 days late. We can look at all this area in here, compute that amount of area, and that will tell us the probability of falling in that range. So let's just talk about a real quick example. Assume we have a normal distribution, which is essentially what we have there. What's the probability of a woman giving birth after her due date? Well, we can see that 50% of the area of that entire distribution corresponds with births after that due date. Here, I'll kind of highlight that for you. We're talking about half of that distribution. So what's the probability of a woman giving birth after the due date? 0.50. It's really that simple when we think about it that way. Area equals probability. Area equals probability. let's go through a couple examples where we can practice working with that concept. Here we have a distribution, and several of the areas underneath this normal curve have been labeled for us. And based on that information, we'll be able to answer some questions like this one. What's the probability of a woman giving birth between 14 days early and 18 days late? So that's highlighted right here with this darker green. Again, underneath this entire distribution is 100% of the scores, 100% of the data for these births. So the probability equals 1. The probability is certain that a birth is going to fall somewhere under there. If I want to figure out the probability of a woman giving birth between 14 days early, which is right here, and 18 days late, which is right here, I just need to figure out how much area is there in this section right here. So we're talking about this section all in here, this section all in here, this green section. If I can figure out how much area there is in that section, it will tell me the probability of a woman giving birth between 14 days early and 18 days late. All right, well, luckily for us in this case, we have some of these other areas actually being labeled for us. Now, later on, we'll learn how to find those areas on our own, but we're trying to start off early and understand the basic concept. So in this region right here, it says this region has about 18% of the total area under the curve. So here's 18% right here. That's associated with people giving birth 14 days early or earlier. It says right here about 12% of the distribution is associated with births in this range, which is more than 18 days late. So how can we figure out the area in here given the information we just talked about? Well, let's think about it. We can add up all the area on the outside of this dark green region that we're looking for. Here we have 0.18 or 18%. Here we have 0.12 or 12%. If we take 0.18 and add that to 0.12, we get 0.30, which is 30%. So 30% of the distribution is outside this area that we're looking at right here. Well, now keep in mind, underneath that entire distribution is 100% of the data, or the probability equals 1. So we should be able to take 1, subtract this value right here, which is all the area on the outside of what we're looking for, and then we'll find what's left in the middle. So here we're going to take 1, subtract 0.30, and again, that 0.30 equals the area outside the region of interest. That's this area right here, 0.18, plus this area in here, 0.12. If we take 1 and subtract those outside areas, we get 0.70 that is left. Well, that area is 70% of the area underneath this normal distribution. That is our answer in terms of the probability. The probability of a woman giving birth between 14 days early and 18 days late equals 0.70. It's that straightforward. If we can compute the area underneath the curve of a normal distribution, we can compute the probability of scoring in that range. Let's go through another example. Here we're looking at the same distribution that we were looking at before with the same labels, but based on what we know about that distribution, let's alter the question a little bit and see if we can figure out the answer. What's the probability of a woman giving birth between 14 days early and 14 days late? So here we're talking about 14 days early, which is right here. And now I'm talking about 14 days late, which would be somewhere right around here. Let me see if I can draw that line. Sorry, I'm using my mouse in this case. That's about as straight as I can draw that line using my mouse. So we're looking for this area all in here. This area all in here. All of this. Okay? Now we're not talking about this little sliver in here. We're just talking about from 14 days early to about 14 days late, which is right here. How can we figure out that area? Well, we do have some clues. We do have a sense of what's going on. Keep in mind, right in the middle, right here, we separate this distribution in half. So from here, there's 50% of the births on one side, 50% on the other. That's going to be helpful in a second to us. And then, of course, we know these other areas right in here. So if I'm trying to figure out this section, how can I go about doing that? Well, let's see if we can figure out how much area there is in this one sliver. This sliver that we don't really want involved in this entire area in here. Because if we can factor that out, that right now is the only area that we don't know. I know how much area there is right here, that equals 18%. I know how much area is right here, that equals 12%. Well, 18 and 12 equals 30, so I know this entire green area equals 70%. Well, what's this? This is what I need to factor out. Well, let's think about it for a second. From 0 to 14 days early, we should be able to figure out that area because I know from 0 all the way out here to the earliest, most premature births is 50% of the distribution. And 18% falls right here. So 50% minus this 18% should show me how much area there is from 0, giving birth right at your due date, to negative 14, giving birth 2 weeks early. So if I take 50% and subtract 18%, so 50% is this entire half of the distribution, minus this part right here, where we already know the answer equals 18%, I find that 32% of the distribution is found between 0 and negative 14. Well, these distributions are symmetrical. So the amount of area from 0 to negative 14, that's from the due date to 2 weeks early, is exactly the same as the amount of area from the due date to 2 weeks late. So in this case, I should be able to take this 32% that I've just computed right here and add that to another 32% because I know it's equal to this value right in here. And then I can find the value altogether, the area altogether. So in this case, I can take 32%, add 32%, and find a value of 64%, or a probability of 0.64. And again, that's because these distributions are symmetrical. If I know that the value from 0 to 2 weeks early equals 0.32, then I also know that the value from 0 to 14 days late equals 0.32. All right, so again, we're just trying to use basic information that we know about the normal distribution to compute some basic probabilities. Here's some final information about these normal distributions. 4 criteria, just in general, that most normal distributions share. In order to have a normal distribution, we need to have a symmetric distribution. So if the distribution is skewed, it's not normal. We know that normal distributions need to be unimodal. And when we're talking about a normal distribution, most of those values are going to cluster around that mean. So that's what a normal distribution is all about. Most of the scores are right around the mean. The very extreme scores on the high end and the low end are much more rare. So that is a normal distribution. That is defining a normal distribution. We're talking about some criteria for a normal distribution. Well, if most of the values cluster around the mean and the values that are very extreme relative to the mean are rare, we should find that large deviations from the mean are rare. So those tails taper off. In other words, we find a distribution that looks like what we looked at here. Most of the scores are right around the mean. There is some variability, but we can see that these scores are relatively rare. That's why this curve is shown very low on the frequency axis. So coming back here, that means that large deviations from the mean are rare, so the tails taper off. We can see here that the tails of the distribution are tapering off. This tail tapers off, showing that these scores are very rare. Here, the distribution is very high on the frequency axis, showing that these scores are quite frequent, quite common. And the final criteria, the data is typically influenced by a combination of factors, such as genetic factors, environmental influences, human, mechanical processes, a variety of factors. So things that form a normal distribution typically have some combination of influences, and that's what typically produces that normal distribution. When we look at some examples, you'll see what I mean. Think about like people's heights. That's clearly influenced by genetic factors, but you know it's also influenced by environmental factors. So your height is influenced not only by your parents' genes that you've inherited, but also by your environment in terms of the exercise you get, the nutrition that you get, all these types of things. So think about something like your SAT score. So that's going to be influenced by some genetic issues in terms of natural ability, in terms of your intelligence, but of course it's also influenced by some environmental variables in terms of how much you've studied and how much you've prepared and how serious you are about it. The same thing like when we're starting to talk about products, things that are not really human and don't have a genetic component. Think about like the size of pens, something like that, or the weight of pens. When companies are trying to manufacture products, they want them to be within certain tolerances. They want their machines to be working the same way as much as possible all the time. Well, here we have mechanical processes, and they're not usually working in exactly the same way at any given time. Even those machines have some slight variation in those processes. So we might find that a typical pen weighs some average amount, but there's going to be some variability from that average. So all of these things that we can measure, pens, CDs, people's blood pressures, SAT scores, in general, the scores are going to pile up around some mean, but there will be some variability from that mean. And ultimately, let's just go back a few slides. Ultimately, when we measure those things, we'll find a normal distribution. So most men are right around 5'10". There are some men who are 6'10", but they're pretty rare. There are some men who are 4'10", but they're pretty rare. That right there is describing a normal distribution. Some of those pens are going to weigh about 2 ounces, but some are going to weigh 3 ounces. They'll be very rare. Some of them will weigh 1 ounce. That's very rare. So that's signifying some problem, really, with the manufacturing process. Again, it's a normal distribution. Most of those pens are going to weigh a particular amount right around the mean, but some of them, because of some goof up essentially in the process, some natural fluctuation in that process, are going to be too heavy. Some of them are going to be too light. All right, well, I think we've talked about that enough for this point. That is the key content from section 5.1, and for now, that is all.